Brian? You gonna start another one? I need two. I'm so important, I need two microphones. Okay, I wanted to thank Brian for a number of reasons, and fortunately I had my travel approved before this fiscal year because ours is very restricted now too. I wouldn't have gotten approval to come here if I had done it in last fiscal year, so that worked out well. It was a collegial honor for Brian to invite me, and so I appreciate it from that standpoint. But I think more importantly, from a personal standpoint, this is, Brian sort of started the ball rolling to get me to Asia. I haven't been here before. And a good friend and colleague of mine at Colorado State University has been trying to get me to come to mainland China for a number of years, and once Brian invited me here for this, then my colleague made all these arrangements for me to go to mainland China, so I'll be going there tomorrow for the better part of a week. So this is really exciting. And then at least for some of the audience, I have a much greater appreciation for all our colleagues who travel from Asia, Australia, and New Zealand to the U.S. and have to, halfway around the world and have to deal with jet lag. And as we say in the U.S., now the shoe's on the other foot, and it really sucks. And but the nice thing is, at least when I get here, I can speak in my native tongue and not have to speak in a second language. So I'm still. So what I'm going to talk about this morning. Let me just, my view of this sort of keynote or introductory presentation, and I'm going to view it more as an introduction to what other people are going to talk about, is to do two things, to sort of set the context for the more the specific science talks that follow, and also to take more of a 50,000-foot view of things, and that's what what I've done in the paper, and that's what I'm going to do here this morning. Obviously, my context or my background or knowledge comes from U.S. agriculture, so I'm going to use that as a springboard, but I think a lot of the things that I will talk about related to U.S. agriculture applies to agriculture in many other countries, although there are obviously some nuances. I'm focusing on sensing in the robotics context, and some of you maybe think you're not working in the robotics area. There may be some of you just very focused on sensors, but my definition of robotics is very broad, so I think it will include just about everybody in this room. I sort of did this high-level analysis using an organizing framework, which I've called typologies, and then used a Swot analysis. You may be familiar with that, looking at trying to identify strengths, weaknesses, opportunities, and threats. And so I'll present some results related to that, which again is more at the very high level, very strategic planning view of what we need to be doing in biosensing and agriculture, and especially related to robotics. And then some final thoughts. Okay, a little bit about U.S. agriculture. Some of you know some of these things, some of you don't. There are about 2.2 million farms, in quotes, in the U.S., and farms are defined as any enterprise that generates at least $1,000 of revenue in a year. So that's a fairly low bar. And incidentally, we now have more inmates in our penal institutions than we have farmers. So we've just surpassed that here. That's sort of a little fun fact you can share with your friends. The average age of producers, of farmers in the U.S. is 57. I was talking to some colleagues at National Taiwan University yesterday, and apparently they think that their average age is a little bit more than that, and I know in Japan it's quite a bit more than that. So this age issue in among our farmers, our producers, is not limited to the U.S., and we may even be a little bit better off. And when I'm saying farmers, I'm talking about people involved in food production, feed production for animals, fiber, which could be cotton or forest products, whatever, and now biofuels. So it's not just food production. Because of this age distribution, or the age distribution may fall out of this, 55% of the farms are fairly small, and if you look at the distribution here in terms of farm size, you see you've got over half the farms way down on that end, and yet the average is way up here over 400 acres. So it's very skewed. And 50% of the farms are operated by retirees, and that's why the age is so high, and or people with a primary occupation outside off the farm. So it's a secondary occupation. In the U.S., we have about a 90-10 rule with regard to production. That is, about 10% of the producers generate about 90% of the agricultural production. I don't know what that looks like in other countries, but that's what we have. We're a net exporter of agricultural products. And just behind the farm gate, or just the production, from a production standpoint, agriculture accounts for about 1% of GDP. But when you include the entire system, post-harvest, so processing, distribution, retail, all those things, it amounts to about 12% of GDP. So it's a significant player in the economy. The other thing about this slide here is if you look at about 1940 to 1980, that's this really steep part of this curve where the number of farmers dropped, and so the acreage per farm increased dramatically. And that'll play out in the next slide. And this just deals, apparently, this is from the Farm Bureau, American Farm Bureau Federation, just dealing with food and not fiber and other things. But you can see the big change in the number of people fed by a farmer over this time span. And the thing that's significant is when you start looking at percentage increases. So from 1940 to 1950, there was a 32% increase. And then 70%, 59, 56. Well, a lot of that is because the farms just got bigger. So each farmer had more land, and so greater production. And as I mentioned from the previous slide, that sort of tailed off at 1980. And there you see from 1980 to 1990, it's 12%, and then 8% and 12%. So I was thinking about this actually very early this morning, and that it's probably, well, in addition to the farm size being largely responsible for this increase, the number of people fed by a single farmer, there were certainly technology improvements. More use of mechanization. There were more use of fertilizer and irrigation, as well as herbicides and pesticides, and biotechnology created better strains, faster growing, higher producing strains. So it's not just the increase in the size of the farms that led to these productivity increases. And it's my sense that probably all this in the last 30 years is related more to science and technology advances. So we're looking at maybe an annualized increase of about 1%. So here's the operational definition that I'm using for biosensing. That is sensing the presence, location, and or characterization of any biological target. And you could be doing that sensing any characteristic of the biological specimen that you're interested in. It could be a chemical signature, for example. So it's a very general definition. And then here's a definition that I'm using for robotics. And first of all, the sensing component, and obviously I think everyone in this room agrees that that's the most important piece. So sensing the environment, and the environment could be a field, an animal operation, a processing facility. It could be part of a distribution network and related to food safety or something like that. And then the system, whatever it is, makes some intelligent decision based on in that environment and the assigned task, and then respond in some productive way. And that could be actuating, informing, or assisting. Now, you probably noticed there's nothing in here about mobility. It's not the case. I don't believe that robotic systems necessarily have to be mobile. They have to be wheeled, or they have to have legs, or anything like that. I mean, that's the common view, at least in the public arena, of robots. But we can have smart roads, smart structures. As I mentioned, smart distribution networks, smart sensor networks of all sorts. So I consider those as part of robotics as well. So the first two bullets up there sort of describe why I think agricultural robotics is really, really important to the problems that we're dealing with. And as I'm sure everyone that's involved in agriculture knows, the agricultural enterprise consumes large amounts of land, water, and chemicals of various sorts. And so it's very resource intensive. Also in the U.S. and other countries, and coming to more countries near you, is the issue of labor availability and cost. And that's a big determinant of how well any particular country is able to compete in the global marketplace. So what robotics can do, and the sensor networks, there are sensors that are part of that, can help agriculture be more productive and effective, reduce their footprint environmentally, both in consuming resources and generating waste. And then on the last one, related more to the economics, or at least to the social side of things, eliminating unskilled, unsafe, low-wage jobs, creating higher skill, higher wage jobs, new enterprises, and which leads to more money in the rural economies and creates a better rural community. And when you add those things together, the social, the environmental, the production, and the economic viability, we're really talking about agricultural sustainability. So I think, I firmly believe that agricultural robotics has a strong role to play there. Okay, now a little bit more about why I've come at this problem from the direction that I have. Brian alluded to this. I'm in an agency called the National Institute of Food and Agriculture, which is in the U.S. Department of Agriculture. And we're a granting agency, a federal granting agency. About half of our money goes out the door in competitive grants. This is our mission statement. So we're focused on both the nation and the world. And we have two roles. This is the program leadership on the program side, myself and people like me, and then we have the grant management side piece here. So within this framework, this is the way we've been spending our competitive dollars in the last 9 years. You see, most of agriculture and food is related to is in the biological science area. So that's where we spend most of our money. A good chunk in social and behavioral, which economics is in here too. Other physical, which might be hydrology and various other things. And it's a very small piece related to engineering. So the money that we do spend in this area, which includes sensors and robotics and a whole bunch of other things, it would be nice if that's well spent, or really moving the needle further over towards agricultural sustainability. So that's why I'm particularly interested in this topic and why I did the analysis here that I'm going to just describe now, and I'll share with you. I'm going to go through it fairly because the paper that's posted is fairly detailed, especially related to the typologies. And so I'm gonna go through those very briefly. You can read those in more detail to understand exactly what I did. But basically, I use typologies, as I mentioned before, as just sort of an organizing framework to lay out some of the components of sensing, the concepts of sensing, etc. And I identified, for the sake of this exercise, 3 typologies, one related to the spatial relationships between the sensor and target. The sensing frequency was the second one, and then the type of sensing that we want to do. And I think I'm sure that if we sat down as a group or individually, if you were to do something different, you'd probably come up with 3 different ones or slightly different variants of these or something. Because everybody has a slightly different way of viewing the world. And as I said, it's not so important on necessarily the typologies you use, but it allows you to organize your thoughts and then feed that into the Swot analysis, which we'll talk about later. And as I was looking at the typologies I was putting together, I noticed that some of them really dealt more with the sensor platform specifically, sort of internally and how it operated. So there was 2 typologies that were more endogenous to the sensors, and then one that dealt more with the external pieces, which is the spatial relationship between that brought in the target much more. And then also, when I show you, and if you had a chance to look at the paper, and you look at the way the typologies are laid out at every branch point, in some cases you'll have contrasting alternatives as you move through the typology. So it's a dichotomous sort of key situation. In other places you'll have characteristic branch points where the lower level elements can be more descriptive of the higher level element, and the higher level element will have some sort of value associated with each of those characteristics. Well, when I thought about this, these are really, the dichotomous one is just a digital 0-1 version of the characteristic one, so there was I didn't feel I had a problem with mixing them. The second part, as I mentioned, is the SWOT analysis. Again, it's strengths, weaknesses, opportunities, and threats. And I use the concepts, issues that I identified in the typologies to come up with some examples. Maybe not the best strengths, weaknesses, opportunities, and threats, but at least some that I thought were reasonable. And then where the rubber hits the road is coming up with some of these final strategies. And there's 2 types: matching and converting. In matching, the idea is to identify momentum opportunities or situations by matching the strengths that you already have with opportunities that the situation may provide you, or appears it provides you. The other type of strategy is a converting strategy, where you try to recast or redirect or sort of think outside of the box and look at the problem a little bit differently, and saying, how can we recast threats or weaknesses into opportunities or strengths, respectively. So that's sort of what the process I went through, the methods, if you will. And here's the first typology, and again, the details are fairly well spelled out on why I did it this way and what these different breakdowns really mean. I looked at, under spatial relationships, where you may have a fixed spatial relationship between the sensors and the target, or a more dynamic one. And the dynamic one, it could be just the moving target, just the moving sensors, or a combination of those. And here under fixed, it could be contact or non-contact. And then a more detailed dichotomy. This is the dichotomy one. It's exclusively dichotomy, where it sort of breaks out as one or the other at each branch point. So that's really all I wanted to say about that, other than what's in the paper. From that particular typology, I came up with this list of strengths and weaknesses. Right now, I think the work that I typically see, and some of it we fund, or I see reports of what people are working on. It seems like our significant strengths are in structured environments and fixed sensing in terms of spatial relationships. Yeah, I mean, that's the simpler problem. It stands to reason that that's what we would be pretty good at. The other strength is that for many plant applications, in crop fields or whatever, the plants aren't going to move around much. And, they may sway in the breeze, but that's a strength of the situation that we have. When we get into the animal production, it's very different. Weaknesses, well, the second one in particular is just sort of the complement of the strengths over here, and that weakness is unstructured environments with changing sensor target geometries is something that is going to be very difficult, or as a weakness. And then another weakness is the existing functionality of embedded sensors in plants and animals. Right now, we don't do that very well. Opportunity. There's a strong market exists for self-navigating equipment, and a lot of that's related to labor issues and accuracy in some cases. And I think because of not that much work, most of the people I know, at least, that I'm familiar with, I tend to work more on the animal side, but I work alongside a lot of I work mostly on the plant side, but I work alongside people on the animal science area, and there's just not that much being done with regard to sensors there at this point. So I think there's a great opportunity for science and technology advancements there. Under threats, obviously there are legal and liability issues. For example, with autonomous mechatronic equipment. That's just one example, but there's others, but there's a lot of legal issues, even when you get into food safety and traceability and all that sort of thing. Who's really responsible when you have a food safety outbreak, when you're detecting it with some sensor network? And then, especially on the food side, there's a reluctance by the post-harvest, post-production industries to increase food costs with better sensors. It's not always clear to them that they're going to get that money back or be able to charge a higher price for having this, this sensor network. For example, food safety. How do you convince people they should pay more for it? Do they know food's going to be safer just because you have a traceback system in place? Here's I've thrown up then, based on this analysis, what one possible matching strategy and one possible converting strategy. A good matching strategy, at least for some of the robotics things when you're dealing with autonomous machinery, is to leverage developments in the auto industry, because they're really moving fast now with driver assist autonomous automobiles or vehicles. And not just on the technology side, which of course most of you are interested in, but again on the legal and social cultural side. How are people really going to use these things? And what are the liability issues? Converting, identify ways to create more structured settings within existing unstructured environments. I think some people are doing that. They try to simplify the problem, but maybe we need to be looking at not just dealing it from a science and technology standpoint, simplifying it, but maybe from a production standpoint. We need to try to simplify the environment to make it more structured, so then our systems will be more applicable. Sensing frequency. Tell you, given the time constraints, I'm going to skip this one and just go to this one. Again, all of this is in the paper. That's a nice thing with having the paper, especially ahead of time. Characteristics to be sensed. I broke it initially into physical and non-physical. And under the physical, there's movement, there's external characteristics, like size, mass, position, etc., and then some structural things, texture, firmness, etc. Non-physical, we have, I looked at considered biological, chemical, as well as visual, and then there's more details there. Under the strengths and weaknesses, opportunities and strengths, or threats, well, I think we're pretty good at structural and external sensing. We've been doing that to some extent in the industrial sector for a long time. And there's a lot of work been done on visual sensing and, RGB color spaces, etc., for a long time. So that's been extensively studied. So I think we have a strength there. We're weak on really a lot of the biological and chemical sensing that we need to be doing, and sensing speed in some cases, keeping up with the pace of production or processing or whatever it might be. There's a lot of, in opportunities, there's a lot of need to have better capability in identifying chemical signatures of the biological targets that we're interested in. And, well, sort of all through this, the applications are so diverse, so that's always, in terms of what we need to actually sense, that's always going to be a problem, but it's one that we really need to think about. And also, on the social side, we have to look at what is currently and what is going to be the technological sophistication of the workforce and the end users, the people that are going to purchase it, and then the people that work for them. So here's a matching strategy related to this SWOT analysis, where I suggest we might consider integrating chemical sensing with other sensing platforms and capabilities to gradually expand the range. That is, we already can do some scanning very well. If we, some of the other technologies that we are pretty good at, and incorporate some chemical sensing as an additional sensor, and do some sensor fusion, and use the other sensing that we're good at to help inform the decision making based on the chemical sensing. So sort of pulling the chemical along with what we already can do pretty well. And then, although I know there's some material scientists here, like Brian, in a lot of cases, there's not, a lot of the projects I see don't necessarily have as much involvement from material scientists or computer scientists, and where we can lean on their expertise to find better chemical biological sensors on one hand, and faster processing and communication technologies. Okay, second to last slide. I'm going to skip the first point. But this is sort of just a preliminary analysis, and like I said, 50,000-foot view of things. Further refinement would be nice. Actually, I'd like to sit down with a group of people and sort of hash some of this out, some of the people in this sensor community, and see what they would come up with. I think it's particularly helpful for me to think about this, and others in the granting agencies, but I think it's also useful for some of the investigators to think along these lines. And at this level once in a while. It really can help direct the work that you do. A recent report came out. It turns out in the U.S. at least that 40% of the food is wasted between the farm gate and the plate in your home, and which is I know there's quite a bit of waste, but that's sort of remarkable. So, I mean, that's in the processing, the shipping, the handling, the storage, the retail. The retailers throw away a lot of produce, for example. And then also once it gets into your home. It's expired, you know, a lot of, well, as you probably know, you know, if you've had a garden, you know, if you pick the lettuce and eat it right out of the garden, after you wash it, of course, that it lasts a lot longer once you put it in a refrigerator, and it tastes better than if you buy it in the store and it's already been sitting around for maybe a week and then it doesn't last very long. So you end up throwing a lot of food out just because the storage, once you get it home, the storage length is not what you would like. And then finally, I think, you know, thinking back to some of the earlier slides, I think there's a real opportunity here for the sensor community to play a big role in maintaining productivity increases. If that annualized increase in productivity is about 1%, so we're talking about 10% every decade or something like that, I think there's a real opportunity there for the sensor community to help with that. And I think when you look back historically, there was a huge impact by the biotechnology and the genetics, genomics, and some of the new breeding technologies in terms of increasing productivity. And I think the impact of sensors going forward in the next 30 or 40 years can be equally as impressive. So I think you've got your work cut out for you, and I wish you luck in it. And there's my contact information. So if you're close enough, you can take it right off the screen, or you can get it from the PowerPoint with your phone. Thank you.